Okay, welcome everyone. It's my pleasure to introduce Marco Gualitieri from the University of Toronto, and he'll talk about realizing the potential of generalized scalar geometry.
All right, thank you. Thank you very much for the invitation and for this wonderful conference. I would like to speak about some recent work in generalized scalar geometry in collaboration with my student Francis Bischoff, who just graduated this year, and with Maxime Zabzin. I think that on generalized scalar geometry, we were stuck for quite a while. In 2011, at the first string math, I gave a talk about generalized scalar geometry. And then I had a period of not working on it because of being stuck. And I gave a talk in string math 2013 about groupoids, which to me was a completely different topic, unrelated, exciting new topic. It turned out that the groupoid stuff was helpful in getting unstuck. And the result of that is what I'm going to speak about today. It's based on this paper, in which we see a discussion of the generalized scalar potential and its relation to Morita equivalence, which is a topic that was invented by... so this is symplectic Morita equivalence as opposed to the algebraic one. This is a symplectic version of Morita equivalence invented by Alan Weinstein and his students. Okay, so let's go back to the beginning of generalized scalar geometry. It all started, somehow this is the beginning of string math in 1979. Zumino was studying the two-dimensional sigma model of maps from a two-dimensional surface into a Riemannian manifold. And he asked a simple question: under what conditions could this model be enhanced into a supersymmetric model? And he observed that if you have a Kähler structure on the codomain, then this model can be viewed as a model with supersymmetry. In 1984, Gates, Hall, and Rocek took a second look at this observation and realized that Kähler wasn't the only solution. There was another possibility, which they discovered, which is the possibility of having a pair of metric-compatible complex structures. Neither one of them is Kähler. The symplectic forms or the Kähler forms are not closed. Normally a 1-1 form, if it's closed, it would mean that it's killed by del and by del bar. Therefore, it would be killed by the difference of del and del bar. The difference of del and del bar is exactly dc. Normally, dc omega is 0 on a Kähler manifold, but in a generalized scalar manifold, neither one of the Kähler forms is closed. But together they're closed in this way. So this indicates which complex structure I'm utilizing to form the DC operator. Neither one of these is closed, omega plus nor omega minus, but DC of omega plus is closed. So we have this pair of conditions. So Gates, Hall, and Rocek presented this to the mathematicians of the time, and the mathematicians just kind of, I've never seen this before. Let's move on. Okay, so there's several questions that come up naturally from this, which they asked in 1984. They asked, is there a Kähler decomposition, just like in the Kähler case? Is there a Kähler potential? There should be, according to supersymmetry. Is there a notion of quantization? And the questions went on. And so our job is to answer all of these questions for this new version of Kähler geometry. Okay, so the first major question I want to discuss today is the notion of Kähler potential. We know that in Kähler geometry, the remarkable thing is that this symmetric matrix, the metric, is a consequence of a single real-valued function. But to be more precise, you need to know the complex coordinates for this fact to be true. You need to have the complex chart and a smooth function in order to be able to write the metric. And Zumino also interpreted this fact. Zumino realized that what you could do is extend your map to a supermap from a super domain into the Riemannian manifold. And then with respect to this super map or superfield, the action of the sigma model becomes just the pullback of the function integrated over the supermanifold. So Zumino's interpretation of this remarkable fact about Kähler geometry was this remarkable fact, that the action is just the pullback of a scalar function. So in this sense, it becomes manifestly supersymmetric. And the first question I want to answer is what the analog of this function is for generalized Kähler manifolds. The problem is that you cannot use the same argument. The usual argument is that omega is closed, and it's del closed, d closed, and so therefore by the dd bar lemma locally you can express it as dd bar of a function. But omega is not closed, so there is no naive argument that gives rise to a function. The second amazing feature of Kähler geometry, my personal favorite aspect of Kähler manifolds, is that they're related to algebraic geometry. So if I have a Kähler manifold, you could think of it from this point of view. So this is maybe a geometric quantization approach to Kähler geometry. You focus on the symplectic form, pre-quantize it by finding a line bundle with a unitary connection whose curvature is omega, and think of the complex structure as a polarization, a complex polarization. This allows you to take half-flat sections or holomorphic sections of the line bundle, and we get a Hilbert space, or a complex vector space. Okay, so this is the quantization of this symplectic manifold. But the quantization procedure depends upon the choice of polarization, the complex structure. And we know that there's a projectively flat connection over the moduli space of complex structures. So that means that this Hilbert space doesn't really depend on the polarization, as we expect in geometric quantization. We don't want the quantization to depend on this auxiliary choice of polarization. Okay? However, if we quantize not just omega, but all integer powers of omega, okay, then what will happen is that we will be taking the holomorphic sections of L squared, L cubed, and so on. Each one of those separately is a quantization. Each one of those separately does not depend on the complex structure, but together they form an algebra, as we know very well, just because of the fact that we keep iterating this line bundle, and therefore we can take tensor products of holomorphic sections. This produces a Z-graded algebra, which does depend on the polarization, as we expect. We know that this gives the graded ring of algebraic geometry, and that contains the information of the complex structure. So there's a question in generalized Kähler geometry, what's the analog of this? I mean, I don't have a closed form, so apparently I cannot just pre-quantize it in this way. And I have two complex structures, and I plus and I minus. Am I supposed to use one, the other, some combination? So all of this is embedded in this question number 2. Okay, so those are the main two questions. Find a potential function and figure out what does it mean to quantize. And is there a relation to algebraic geometry? Okay, the main tool that I'm going to use in order to answer these questions is generalized complex structure in the sense of Hitchin. So a generalized complex structure is a complex structure on the extended tangent bundle T plus T star, which is involutive for a certain bracket called the Courant bracket, which exists on this bundle. And here are the 3 main examples. If we arrange a symplectic form, if we view a symplectic form as mapping from tangent to cotangent, and if we take its inverse to go from cotangent to tangent, we can arrange the symplectic structure in such a way that it produces a complex structure on this extended bundle. That's the first example. Second example is the diagonal example, where we have a complex structure acting diagonally, one on each factor. And the third example is a deformation of this one, where I turn on an upper right element, Q, which maps from T star to T. And this Q is the imaginary part of a holomorphic Poisson structure. So you can check that if I have a holomorphic bivector field, okay, I can place its imaginary part here, and this matrix will square to -1, and it will be involutive with respect to the Courant bracket. So this explains that, for example, a complex manifold can be deformed in the space of generalized complex structures to something which is not a complex manifold, but something which is more general than a complex manifold. And all right, so why is this structure relevant to the problem, to this problem of generalized Kähler structures, where we have two complex structures and a metric? So the answer to that was explained to the audience of String Math 2011, and that is that if we take the complex structures and arrange them in this matrix, what we obtain is a pair of generalized complex structures. So this complicated structure discovered by the physicists can be rearranged into a complex structure on T plus T star, two of them, one using the plus and one using the minus sign. And the important thing about these two is that they commute with each other. Unlike the two complex structures, which don't commute, they have no a priori algebraic relationship with each other. So we have a pair of these generalized complex structures which commute and which together, using the natural inner product on T plus T star, give a positive definite generalized metric. And this is an equivalence. So there's an equivalence between generalized Kähler structures and this bi-Hermitian data. So this point of view on the geometry brought to the fore many new structures that are embedded in those equations, which help to solve the two problems that I'm discussing today. So let me just give you some information about that. So there's an interesting feature, which is that whenever you have a generalized complex structure, the top right corner, which maps from T star to T, it's always a Poisson structure. So part of generalized complex geometry embedded inside it in a very kind of integral way is Poisson geometry. And this is always a Poisson structure. So let's look at those. So I wrote them here. These are those two Poisson structures. And these are this is a picture describing the symplectic leaves of these two Poisson structures. Now, these two Poisson structures, each of them has symplectic leaves, and I can take the intersection of the two symplectic leaves, and I get a new foliation, okay, the intersection foliation. And on that intersection foliation, I can take the difference between the two symplectic forms that I get from the red and the blue. And so this will have the difference of the symplectic forms. And it turns out that that difference is always symplectic, and it always defines a new foliation, which is also a Poisson structure. So there's a third Poisson structure, which was discovered by Hitchin, which is obtained by taking the commutator between the two complex structures and combining with the metric. And so this tensor is the imaginary part of a holomorphic Poisson structure with respect to I plus and with respect to I minus. This is very complicated, and you don't need to follow the details. The important thing to remember is that embedded in this geometry, by combining the complex structures and the metric in some unexpected way, what pops out is a holomorphic Poisson structure with respect to I plus and with respect to I minus. In the usual Kähler case, this Poisson structure is just the inverse of the symplectic form, and this one just vanishes, and this one vanishes too. And so you don't see this feature in usual Kähler geometry. It just drops out. Okay, so basically this geometry is like a deformed Kähler geometry. You can deform it into one of these generalized Kähler, and it has a holomorphic Poisson geometry embedded in it. Let me give you an example of how to construct such a generalized Kähler. Suppose that you start with CP2 with its standard Fubini-Studi symplectic form, and suppose that you pick a holomorphic Poisson structure, which is just a section of O3. I've drawn its zero set. So there's one big symplectic leaf, which is the complement of this cubic curve, and then the other symplectic leaves are the points on this curve. So this CP2 it's a Kähler manifold that has a holomorphic Poisson structure on it. Take the Poisson tensor and the symplectic form, combine them together, that gives you a class in H1 of the tangent bundle. H1 of the tangent bundle is 0. Therefore, I can trivialize this in the Dolbeault complex. There is some smooth vector field whose d bar is exactly this class. I can choose V so that it commutes with the Poisson tensor. So this smooth vector field is what I try to draw in orange here. It's some smooth vector field on the CP2. And it's related to the Poisson tensor and the Kähler form by that equation. Take that smooth vector field and take its time one flow, apply it to the complex structure. What we get is another complex structure. Not equal to it. It's isomorphic to it, of course. We're talking about CP2, but it's not equal to it. So we have two distinct complex structures on the manifold. And then what we do is we take the time one average of the flow applied to the Kähler form. That gives me a new two form, omega bar. And then I combine omega bar with the complex structures to get a metric. And it turns out that this is satisfying the equations of motion. So this is a kind of a complicated procedure which produces a generalized Kähler structure. But what I want to emphasize is that this vector field, which is smooth on the CP2, is actually holomorphic when I restrict to the zero set of sigma. Because if this right-hand side is zero, then V is d bar closed. So what that means is that this flow construction restricts to the elliptic curve to be a holomorphic translation on the elliptic curve. And this Fubini-Study metric, which I could think of as representing the O1 line bundle, restricts to this elliptic curve to give a line bundle of degree 3. Therefore, the data that I'm using to build this GK structure is the same data as that which you would use to produce a non-commutative CP2. To produce a non-commutative CP2, it's well known that what you need is an automorphism of an elliptic curve and a degree 3 line bundle on that elliptic curve. So right away from this example of a construction, what I'm indicating to you is that there seems to be a close relationship between this geometry and non-commutative CP2, or non-commutative algebraic geometry. Okay, so I've basically set the stage. That's the summary. What we want is a generalized Kähler potential. We want a pre-quantization. And the key geometric input that I want to use is a holomorphic Poisson structure. Okay, so any questions about the setup and what we want to do? This is what I want to explain. What I mean is that the coordinate ring of CP2, that's a polynomial ring in 3 variables. It's a graded algebra. Okay, and that algebra should be deformed to a non-commutative version of that. That has been studied by Tate, Artin, and Vandenberg. Okay, and they described such deformations in terms of an elliptic curve, a translation, and a line bundle of degree 3. So that data can be used to produce such a non-commutative coordinate ring. Okay, so in order to explain the solution to these two problems, I need to tell you about the usual Kähler potential for a usual Kähler manifold. This is something that everyone knows very well, but I'm going to describe it to you in a slightly bizarre way. And this is a way that you can find in a paper of Donaldson. So suppose that we have a Kähler form, and we write it as dt bar of a function locally, k sub alpha. So k sub alpha is the Kähler potential. Okay, and so that's d bar of a 1-0 form, which I'll call A alpha. A alpha is a local 1-0 form. A alpha is obviously not holomorphic, but if I take A alpha minus A beta, then because both of these d bars are the same, d bar of A alpha beta is 0. So what we have is, on double overlaps, we have a holomorphic 1-0 form, A alpha beta. And of course, this is no surprise. This is just a check representation of the Kähler class. But what I can do with this A alpha beta is just holomorphic 1-0 forms on double overlaps. So I can take that 1-0 form and use it as an automorphism of the holomorphic cotangent bundle just by translating vertically in the fibers. So I take the holomorphic cotangent on U alpha and on U beta, and then I take a covector and shift it up by A alpha beta. And that defines a gluing map from T star to T star. And because of the fact that this is a cocycle, this is a well-defined global gluing, I take all these pieces and I glue them together and I get a global manifold. So the result is of taking all these cotangent pieces and gluing them by this gluing map is that I get a global space, a complex manifold, Z. I've drawn it here. Okay. It is not a vector bundle because this gluing map ruins the zero section. I tried to draw it here that a straight line gets sent to whatever the graph of A alpha beta is. So the zero section is ruined. And on the other hand, because this addition of a one form commutes with addition by other one forms, because the addition in the fibers is commutative, it is an affine bundle for T star X. So this space is nothing but an affine vector, an affine bundle modeled upon the holomorphic cotangent bundle. Not only that, but it because of the fact that these gluing maps preserve the holomorphic symplectic form, what it means is that I get a holomorphic symplectic structure on Z. So this is a holomorphic symplectic affine bundle over X. Now, remember that although this cocycle is of course non-trivial in Čech cohomology, but it has a trivialization in the smooth sheaf of 1-0 forms. And that means that these A alphas, they group together to give a global section of this affine bundle. But this section is not holomorphic. It's a smooth section. This C infinity section, I call it L. Okay, it's just the graph of the derivatives of the Kähler potential. And if I take the symplectic form and I restrict it here, then as it normally is the case, what you get is the derivative of the one form. So whatever that one form is, the canonical symplectic form restricts to give its derivative. And the derivative of this is just d bar of this, which is the Kähler form and which is therefore real. So what we have is that this holomorphic symplectic form restricts to L to give a real symplectic form. What that means is that this C infinity cross-section is Lagrangian for the imaginary part and symplectic for the real part. So Donaldson had observed this setup, and he called this an LS submanifold because it's both Lagrangian and symplectic for the imaginary and real parts. But we know this as a brane in the A model. So we know in the A model that in order to be, so if I take the imaginary part of this holomorphic symplectic form, I'm going to think of this as a real symplectic form, and I'm going to take the A model of that. And therefore, because this is Lagrangian for the imaginary part, this Lagrangian gives me a brane in the A model. So this, what we see here, is a global picture of the Kähler potential. This is how I claim, this is how you should think about Kähler metrics. You should think that the Kähler class is embedded, is incorporated into this complex manifold, Z. And which particular metric you choose in that class is described by this A-brane. You move the A-brane, you change the Kähler metric within its Kähler class. That's how it works. And once you describe it this way, it's obvious why the Kähler metric depends on a real function. It's because it's a Lagrangian, and therefore you can use a generating function to change the Lagrangian. So it becomes obvious, transparent from this point of view, why a Kähler metric depends only on a single real scalar function. That's why. That's one of the reasons why Donaldson thought this was an attractive picture of Kähler geometry. Any questions about this setup? So this is just a twist on something you know well about Kähler geometry. I'm not forgetting it. I'm just noticing that it is an A-brane for the imaginary part. So it's a brane in the A model. Yes? No, of course the Kähler potential will not exist globally, but this Lagrangian will. So the point is that if you wish to describe this Lagrangian locally, then what you could do is you could choose Darboux coordinates and describe this Lagrangian as dt bar of a function. But globally, we can't. And so that's what I mean, that this Lagrangian is the global incarnation of the Kähler potential. Okay, so here's an example. Take CP1 with the Fubini-Studi metric. So my students would probably get me fired if I described this way. If this was the first way that you encountered Kähler geometry on CP1, you probably wouldn't last very long in a classroom. But let's start by taking this affine bundle over P1. This affine bundle is an affine quadric surface. So unlike the cotangent of P1, this thing is actually affine. It's this typical hyperboloid inside 3 space. And it has this equation in C3. And the holomorphic symplectic form can be described this way. And it has an anti-holomorphic involution by taking xyz to its complex conjugate. And the fixed point set is a 2-sphere. So here we have exactly the situation that I described before. We have a affine bundle for the cotangent bundle of P1. That's this space. The cotangent bundle of P1 acts on this. And we have a smooth but non-holomorphic cross-section, which is this real locus. And this is one way of describing the Kähler metric on CP1. Okay, so if this is how we're going to think about Kähler geometry, if this picture is how we're going to think about Kähler geometry, how are we going to think about generalized Kähler geometry? Well, the hint from before was to use Hitchin's Poisson structures. That the new ingredient here, we still have complex structures, just like we have here. We use the complex structure to build this Z space. But the new aspect is Poisson structures. So how are Poisson structures going to modify this picture? Well, for this, I need to introduce a concept that is at the heart of the activity of the Weinstein school of Poisson geometry. So Weinstein's idea was, suppose you give me a Poisson structure. Poisson structures are somewhat annoying because they have all these different symplectic leaves of different dimensions. It's kind of complicated. So Weinstein's idea was, why not find a symplectic manifold that maps to the Poisson manifold in such a way that the Poisson structure, the invertible Poisson structure, maps to the non-invertible Poisson structure. So this is a kind of resolution of singularities for Poisson structures. He proved that in many cases and always locally this exists. But the interesting thing that he observed was this. Suppose that we find a symplectic realization of a given Poisson manifold that's described by this pi map. Then you can always take the fibers of this map, and take the orthogonal complement. That's what I drew in red. And this orthogonal complement actually is involutive, describing another foliation which gives a projection onto a second Poisson structure. This is the kind of remarkable fact that they observed. What it means is that if you symplectically realize a given Poisson structure, what you've secretly done is you've symplectically realized a second one. And this symplectic manifold somehow maps to both of them. And so they axiomatized this into what's called a Morita equivalence between the two Poisson structures. So they defined this Morita 2 category. So let me just quickly describe the setup. So we have objects which are Poisson manifolds, X prime. And now we're going to think of a morphism between them as being a symplectic manifold, mapping to both of them via Poisson maps. This is a Poisson map and this is an anti-Poisson map, in such a way that the fibers of the two maps are symplectically orthogonal to each other. So what that means is that if you take the sheaf of functions, the functions on the left, and pull them back, that will give you a Poisson subalgebra of the symplectic algebra of functions. If you take the functions on the right, the same thing. You pull them back, you'll get a Poisson subalgebra. And these two Poisson subalgebras Poisson commute with each other. They're the Poisson commutant of each other. That's what this orthogonality means. And then we could say that given two morphisms, Z1 and Z2, or Z and Z prime, then isomorphisms between them, isomorphisms of symplectic manifolds, would be the two morphisms. Okay, so you could also ask, Well, okay, I mean, once you describe this two category, you could say, well, suppose that I fix a Poisson manifold. Then what are the morphisms from the Poisson manifold to itself? That's called the Morita-Picard group. And they studied, so this is an object of study inside this field. And there's an identity element. There's a kind of canonical symplectic realization of any Poisson manifold such that if I take the symplectic orthogonal and I look at the secondary symplectic realization, it's actually over the same space. This is what is called the Weinstein groupoid of X. So there's a lot of papers in the Poisson geometry community which focus on the study of this Weinstein groupoid. So let me just give you an example of this Weinstein groupoid. So suppose we take a Lie algebra. The dual of the Lie algebra is one of these annoying Poisson manifolds because it has the foliation by coadjoint orbits. The coadjoint orbits are the symplectic leaves. So it's very easy to produce a symplectic realization by actually integrating the Lie algebra to a Lie group and taking the cotangent bundle of the Lie group. If you take the cotangent bundle of the Lie group, then given any covector at any point, you can always left translate it to the identity, and that will give you a point in the dual of the Lie algebra. So there's a left mapping from this cotangent of G to the dual of the Lie algebra sitting over the identity element of G. And it turns out that that map is a Poisson map. And similarly, the right translation is an anti-Poisson map. So that means that if you were annoyed by having to compute the KKS Poisson structure on G star, well, you can just take the cotangent of G and just use the canonical Poisson bracket on that, and you're golden.
Are you assuming that the algebra has a Lie group?
Yes, definitely. Okay, so this brings me to the main theorem of our paper. So I'm now going to use this idea of Morita equivalence in the topic of generalized Kähler structures. I'm going to apply it to generalized Kähler structures. So if you take a generalized Kähler structure, remember that we have that part of the data is that we have a complex structure I plus, and we have another complex structure I minus. And each one of these has a Poisson structure, the Hitchin Poisson structure. That's the structure that I described before. So for a long time, we were puzzled by the correct relationship between these two complex Poisson manifolds. It is not correct that they're isomorphic. So for example, we have examples where this could be, for example, P1 cross P1, and this could be the second Hirzebruch surface. They're diffeomorphic, but they're not isomorphic. So these two are not isomorphic as holomorphic manifolds or as Poisson manifolds. But what our theorem says is that they are holomorphic symplectic Morita equivalent. In other words, there is a manifold Z, which is holomorphic symplectic, which maps down to both of them by Poisson and anti-Poisson maps. So the correct relationship is that these two are Morita equivalent. So the fact that they're Morita equivalent and having these two maps, I've drawn the fibers of the maps in red and blue. The question is, what about the metric? So far, I've only discussed the holomorphic structure and the holomorphic Poisson structure. It turns out that in order to extract the Riemannian metric, what you need is a cross-section of both of these fibrations. And that cross-section must be a brane, which is Lagrangian for the imaginary part and symplectic for the real part. So this is exactly the picture of Donaldson, but deformed by the Poisson structure. We have a holomorphic symplectic manifold. We have a brane bisection of it. It's just that in this case, the source and target maps, in the previous case, they were the same map. We only had one map mapping down to the Kähler manifold. Now we have two maps, and they are symplectically orthogonal to each other. Okay, so this is the picture. Let me explain a little bit of how this picture works. So suppose that we wanted to go backwards. Suppose I gave you a picture like this. How would you recover this complicated generalized Kähler geometry? Well, I'm just losing my battery here. Do you see that? No. Oh, you see that. Okay. All right, so suppose that, suppose I gave you a picture like this. Okay? Then the kind of first thing to notice is that because L is a cross-section of both of these maps, it defines a map from the left side to the right side. So I can take a point on X minus, look at its pre-image under the S map in L, and then map it forward by T. And that will give us an actual diffeomorphism from X minus to X plus. So as long as you have this cross-section, it enforces the fact that the two holomorphic Poisson manifolds are diffeomorphic. But because this cross-section is not holomorphic, it's only smooth, that means that this will not be an isomorphism as holomorphic Poisson manifolds, just as smooth manifolds. The other cool thing is that because L is transverse to the red foliation, the red foliation will induce a complex structure on L, because L is normal to a complex distribution. So I'm going to get a complex structure because of the fact that it's transverse to the red leaves, but it's also transverse to the blue leaves, so I get a second complex structure. Normally, this wouldn't happen in a complex manifold because you would assume that L is holomorphic. And of course, it would inherit the same complex structure. But in this case, we get two different complex structures. Then we take the holomorphic symplectic form and restrict it to L, and we get something which is real. This real tensor, I can take its 1-1 part with respect to I plus. I can take its 1-1 part with respect to I minus. Combine these together, and what I get is two symmetric tensors, just like I would get in Kähler geometry, but the two symmetric tensors are equal. The reason they're equal is because of the fact that these two are symplectically orthogonal. So we get a single metric from this. Okay. Oh. Okay, so how do I clear that? Clear. Just push clear, yeah. All right. So, thank you. So, right. So now let's. What about the potential function? So how does this solve the problem of the potential function? So, it solves it in the same way that the potential function can be extracted in the Kähler case. So, in order to see this Lagrangian as a function, in terms of a generating function, what we need to do is to choose Darboux coordinates. This is the key thing which was such an impediment for such a long time. In the cotangent bundle case, we have a natural choice of Darboux coordinates. But in this case, we don't. We need to choose them. So if you choose Darboux coordinates in a neighborhood of this Lagrangian, we can write it as the graph of a 1-0 form, but that won't be holomorphic. All we know about it is that its derivative is real. The fact that its derivative is real means that its imaginary part will be exact locally, and therefore d of a function. And therefore, this restriction of the holomorphic symplectic form, this 2 form that we have on L, will be dd bar of this function. So just as in the Kähler case, you need to choose a Darboux coordinate system on this holomorphic symplectic manifold in order to see this Kähler potential function. And this is the reason, essentially the reason, why the physicists were so confident that there was a single function, a degree of freedom for that metric. Let me just give an example very quickly of how you could implement this kind of explicitly. So if I have C2, I've written now a toric Poisson structure, just x del x, wedge y del y. So this is a toric Poisson surface. It turns out that we can explicitly write the symplectic groupoid or a symplectic realization for it. This Z space has coordinates x, y, a, and b. You could think of a and b as being like generalized momenta. And I've written the source and target maps explicitly in terms of exponential functions. I've written the holomorphic symplectic form on Z explicitly. And as you can see, it's already in Darboux form. Then I can pick any Kähler potential function of the x and y coordinates, So I've divided my coordinates into positions x, y, and momenta a, b, and I can pick any Kähler potential that I wish. Just for simplicity, I'll choose it to be T2 invariant, and in fact, I could pick exactly the same Kähler potential that I would for P1 cross P1 as a Kähler manifold, or I could take exactly the same Kähler potential function as I would for CP2. So the Kähler potential, I can pick it to be exactly the same as I would in the Kähler case. The thing I've changed is the structure of Z. It's no longer the cotangent bundle, but it's a deformed version of the cotangent bundle. And if you work out the prescription of taking dd bar of this function and placing it on this Lagrangian brane, then we get a very simple construction of generalized Kähler metrics, which satisfy all of the conditions. So this is by far the simplest construction of a generalized Kähler metric. Okay, so this is the solution of the generalized Kähler potential problem that we presented in our paper last year. Now, with the remaining, what do I have, 10 minutes? Yeah, 10 minutes. I want to describe how you could possibly quantize. So whenever I need to quantize something these days, I refer to my favorite paper about quantization, which is this one. And everything you would want to know about quantization is contained in the first 7 pages of this paper, and then and I highly recommend it to everyone. Gukov-Witten in 2008. What is their idea? So their idea, so they wanted to answer the following question in a new way. So they wanted to quantize a symplectic manifold, M omega. Their idea is the following, and you bear with me. It seems like a crazy idea, but it appears to work. So you take the symplectic manifold and embed it into a complexification. This is a holomorphic symplectic manifold, such that when I restrict this to the symplectic manifold, what I get is something real, namely just the symplectic form. Notice that this thing is Lagrangian for the imaginary part and symplectic for the real part. This may be familiar. So what they observe is that now inside Z, if we think of the A model of the imaginary part of omega, we have 2 branes staring us in the face. One of them is this Lagrangian brane. The other one is this space-filling brane, the canonical coisotropic brane. And what they propose is a vector space, which is the homomorphisms between these 2 branes using open string A model, and they get a vector space, which is the quantization of M omega. That's the idea. So I wish to abuse their proposal. So instead of using they were concerned about having this be the complexification of M. The reason they wanted this to be the complexification, they wanted an anti-holomorphic involution which fixes M. That would endow H with a Hilbert space structure. I'm not so concerned about the Hilbert space. I just want a complex vector space. So the idea is take homomorphisms in our Morita equivalence between the Lagrangian brane, which defines the Kähler metric, the generalized Kähler metric, and the canonical coisotropic brane, which is given by the fact that it's a holomorphic symplectic manifold. This is the proposed quantization for a generalized Kähler manifold. Now, the interesting thing about this setup is that we are working with a quantization which is built from a Morita equivalence. And Morita equivalences between Poisson manifolds, they form a category. They can be composed. Okay? And the composition of 2 of these Morita equivalences is produced by taking their fiber product over the common base and reducing by a coisotropic, by the fact that it has a characteristic foliation. It's basically a symplectic reduction of these 2 symplectic manifolds. And therefore, the relationship between 2 Morita equivalences and their composition is a Lagrangian relation. The fact that it's a Lagrangian relation should mean that in the A model, we get composition maps. So if I have, we get basically a monoidal structure. If I have an object in the Fukaya category of 1 and an object in the Fukaya category of the other, I can tensor them together and get an object here. Okay, so then something very special happens if I take a Morita self-equivalence. If I choose this Morita equivalence to be a self-equivalence, then what I can do is iterate it. I can compose it with itself. and I produce a sequence of Morita self-equivalences. Okay? So this is supposed to be the analog of taking a line bundle in the Picard of a complex manifold and tensoring it with itself and getting a sequence of elements in the Picard. I take an element in the Morita Picard and I iterate it. I take its fiber product with itself many times. I get a sequence of holomorphic symplectic manifolds of higher and higher Chern class, in a sense. And in each one of these, I have two branes. The Lagrangian brane, which describes a generalized Kähler metric, and a space-filling brane, because of the fact that it's holomorphic symplectic. And I can use the Gukov-Witten procedure to take its homomorphisms from one to the other. I get, therefore, a sequence of vector spaces. And because of the composition structure that I explained, there will be a composition on these morphism spaces. So that means that if I take some homomorphism of degree k and a homomorphism of degree L, I can tensor them and get a morphism of degree k plus L. This all comes from the fact that I iterated a single element in the Morita Picard. To give you an example of actually implementing this, the simplest case would be to define one of these Z spaces which lies over P1. So I'm going to take a Morita self-equivalence from P1 to itself. And it's defined by an automorphism of P1, phi, and a line bundle over P1. So the basic idea is that this space is the twisted cotangent bundle with Chern class K. Okay? It has one map down to P1, which is the projection map, another map, which is the projection map followed by an automorphism raised to the kth power. So these two maps, while they have the same fibers, they're slightly different maps. Okay? We can take this holomorphic symplectic manifold, pre-quantize it, and try to come up with a notion of homomorphism between the space-filling and Lagrangian brane. We have a prescription for this homomorphism, which actually provides, as an answer, just the holomorphic sections of OK. So in the end, for each level K, the homomorphisms between these two branes should be given by sections of a holomorphic line bundle over P1. And then the interesting thing is that when you compose these things, because of the fact that this Morita equivalence is non-trivial, this translation, this automorphism of P1 comes into the composition, and what you end up with is a non-commutative product between two sections, which instead of just tensoring the two sections together, you apply this automorphism k times if f has degree k. This non-commutative deformation of the coordinate ring of P1 is called the Vandenberg twisted coordinate ring, and it has this commutation relation. So it looks, if you restrict it to the, if you restrict it, yeah, so it just looks like what's called sometimes the quantum plane, or the Q-deformed plane. Okay, so just to conclude, this explicit description which I gave here for P1, we have a generalization of this to toric Poisson varieties. I should put here Fano varieties. So if I have a toric Poisson Fano variety, we have an explicit description of this Morita self-equivalence and its brane structure and so on. We can take its iterations, so we get a sequence of these holomorphic symplectic manifolds. Each of them has two branes in them. We have a proposal for how to extract this vector space of A-model homomorphisms. And this gives a sequence of holomorphic sheaves on the original X, complex manifold X, this toric Poisson variety. And what we get when we take the composition of these is we get a non-commutative algebra which can actually be described as a sheaf of non-commutative algebras deforming the structure sheaf of the toric variety X. But the sense in which it's a sheaf is that it's only a sheaf for the topology of torus invariant open sets. So for each torus invariant open, it associates a non-commutative algebra. And for every intersection of such, we get an isomorphism between non-commutative algebras. So instead of the analytic topology, we get something that looks more like the Zariski topology, but which is even more coarse than it. The challenge, which I'll leave with you, I don't have the last slide. The challenge for future string math will be to generalize this to the non-toric case. In the non-toric case, we do not have an explicit description of the self-equivalence. And it is not isomorphic to a twisted cotangent bundle. It has a much more complicated topology. And we don't have a proposal for the homomorphism space in the A model in that case. Although the procedure tells us exactly what we should be computing a sequence of homomorphisms in the A model in order to get a non-commutative algebra. We simply don't know how to compute the answer. So I'll leave you with that. Thank you for your attention.
Any questions? No? Yeah, over there.
You had the form is irreversible, right? So you had an assumption that this F exists.
Correct, yeah.
So what happens if it doesn't?
So, for the purpose of this talk, the reason why this assumption was there, you're referring to this assumption, is that from the point of view of generalized Kähler geometry, what I wanted was for one of the two generalized complex structures to be symplectic. So this is what we call the symplectic type. So what that means is that it's like if you take a Kähler manifold, you retain the symplectic structure, you keep it, but you take that complex structure and change it to a generalized complex structure. That's what's happening. And the reason why it's important for the point of view of my talk is that it's like what you're doing in Kähler geometry is that if you want to relate it to algebraic geometry, you're doing geometric quantization of the Kähler structure. And that's essentially what I'm doing here. I'm also geometrically quantizing the Kähler, the symplectic structure. So I need that symplectic structure to be present. And the generalized complex structure, this deformed complex structure, that plays the role of the polarization. And what I get is this algebra, which is highly dependent on the polarization. Okay, so in the more general case, the relationship between the two complex manifolds is more complicated. They're no longer Morita equivalent, and there isn't a symplectic picture. There isn't a symplectic form in the picture. So there's still Morita equivalences in the picture, but the Poisson structures are not Morita equivalent. There's these things called Dirac structures on each side, and those are Morita equivalent. So while we have a description of that, we don't understand it nearly as well, and we also don't have an understanding of what it could mean from the point of view of algebra. So we have no proposal for what is the analog of algebraic geometry in that case. Yeah.
Any further questions? Yeah, just one quick question there.
It's here. Oh.
In your Morita equivalence that showed up, you mentioned that there were Lagrangian relations appearing
yes.
At some point, but if I'm remembering was the Weinstein category, there were many problems with the composition of the morphism. Is there any kind of such things that appears here? We have also many problems, and also members at the quantization, one of the quantizations that was produced was the Warham-Woodward category. And I was wondering if it was any close to what...
Yeah, so any time that you have symplectic reductions, you get Lagrangian relations, and the Warham-Woodward category is important for that if you want to quantize it to a Fukaya. So it's all within that sphere of ideas, yeah. I mean, the central idea of Gukov-Witten was that we should use the A model in order to quantize symplectic manifolds. That's the idea. So to whatever extent you know the A model, whatever the complexities and subtleties are, and of course there will be the major obstruction here to our progress is that we don't understand mathematically how to take morphisms between coisotropic branes. That's the main problem. Yeah. So it's only in these cases that we have proposals and guesses for how to compute those in these cases. That's the reason that we can get these answers. But in general, there are very few guides in the physics literature for how to compute morphisms between coisotropic A-branes.
Okay, I think we need to move on, so let's thank Marco again.